All right, now we can get started with the next section, which is going to be focusing on maps for autonomous driving. And specifically, we will be talking about different types of maps, both sort of high-level sparse topological maps, as well as the so-called HD maps that you keep hearing on and on about. For those of you joining us later, my name is Andre. I've also been covering the hardware section previously. I'm a research scientist in Waabi, and on a daily basis, I mostly work on state estimation and localization, and I also do a fair bit of work in sensor simulation. So there are basically two types of maps that are used in self-driving. There are topological maps as well as high definition or HD maps. And in this talk, the goal is to kind of give you an overview of what these are and how each of them is useful for autonomous driving, as well as, of course, how to actually create them. So in the first section, we'll focus on these so-called topological maps. Topological maps contain a diverse set of attributes, such as the road topology, the number of lanes in a street segment, certain building footprints, the locations of key landmarks, and so on. And they're typically used in two major ways in autonomous driving. First, they can be used to get an understanding of the potential difficulty of a given area. So for example, trying to figure out where it's profitable to operate, whether that's ride sharing or freight or whatever, and trading it off with the complexity of the domain. And second, they are also used online by the self-driving vehicle itself in order to help plan a high-level route to go from point A to point B, just like a human will use, Bing Maps, OpenStreetMap, Google Maps, Apple Maps, whatever. Topological maps can be produced from a very wide range of data sources. One immediately available kind of data is dashcam footage collected from fleets of vehicles, because these kinds of data sources are widely available. People use them all the time for insurance purposes, for example, and there's actually companies that try to build these crowdsourced maps, and it's quite an effective techniques. You can also use drones, planes, satellite footage, whatever. There's, again, entire companies whose entire role is to provide people with up-to-date information from these kinds of modalities. And of course, if you have self-driving vehicles, whether they're ride-sharing vehicles, whether they're trucks, maybe you're running your own drones, whatever, you can also use these to collect data as they operate, and then use this data to build some sort of map representation. And one of the basic tasks of this topology estimation is road topology extraction. And in the literature, there are kind of three major families of methods that you can use when it comes to extracting this kind of road topology. So the first one would be basic segmentation, followed by heuristics. Then you would have energy-based models, also a classic form of inference. And then, of course, you have neural network-based, which is the most kind of recent family. And of course, it has a wide number of sub-approaches. So for the first category of segmentation-based models, the main idea here is you apply some sort of existing architecture for pixel-wise semantic segmentation. Maybe you do a binary segmentation. Is this pixel a road or not? You might do multi-class segmentation, for parking lots, buildings, whatever, or predict other attributes. And then you post-process this information in order to obtain an actual map, some sort of topology, some sort of graph. And these methods have a fair number of benefits, including the fact that you can piggyback off the latest, greatest semantic segmentation models, leverage those architectures, maybe retrain them for a purpose, and then get really good performance in this pixel-wise segmentation. But this can also be a weakness, because essentially the road network extraction that you're doing downstream kind of depends on the quality of your semantic segmentation and might have difficulties correcting for mistakes here, because in essence, this is kind of a cascaded approach. So for example, if there's occlusions, if there's building shadows, trees occluding the road, and the segmentation isn't great in a certain area, the actual extraction of the map might fail. And of course, you're also dependent on this post-processing algorithm, line fitting or whatever, which might be okay to set up at first, but might quickly grow to be difficult to manage because of a lot of rules and exceptions that are kind of hand-tuned. There's also the great family of energy-based models, which is the next category. And here, rather than just sort of doing this cascade of semantic segmentation that you then post-process, the idea is that you build some sort of graphical model using potentially segmentation priors, as well as maybe some geometry priors, and then you run inference in this model. So here you're basically casting your road topology extraction as an energy minimization task. And this allows you to have a lot of flexibility into how you're specifying a lot of the requirements of the road network without necessarily having to commit ahead of time to your semantics. So we have an example from a paper by Matthews et al. That uses this kind of formulation to take OpenStreetMap road center lines without any additional information, and then leveraging information from aerial imagery, leveraging some additional priors, they actually predict the road width. And then they kind of augment this skeleton that you get from OpenStreetMap with additional information. And this is done, again, using image edges. It does a bunch of stuff with semantic segmentation of the aerial imagery, as well as processing the input graphs themselves. And while mathematically more structured, these methods can still sometimes need to rely on these handcrafted features and might sometimes fail to produce the high fidelity that we really need for autonomous driving, especially when it comes to very, very complicated outputs. And a learning-based approach that is fully learned more or less end-to-end can help alleviate some of the limitations we just saw, like the need to handcraft heuristics. So a lot of recent papers in the last 4 or 5 years have been leveraging first recurrent, then graph neural networks, and more recently transformers to directly predict your topology graph. And this can be done, again, you can just have like a network output it, or you can draw it iteratively. So there's papers that use, for instance, a recurrent network to iteratively predict the next vertex of a road polyline, and then kind of try to figure out what the polylines are, and then kind of process them sequentially. Or you can use things like graph neural networks to extract building footprints kind of in one shot and predict a polygon that is very compact and editable and so on. But there's some challenges with these networks, especially with recurrent nets. That they can sometimes be difficult to train. And because of the way they do inference, they can be slower than other approaches. But in the recent years, because of the advent of transformers and with the hardware benefits that come with them, some of these challenges are being overcome. So a lot of newer methods actually are powerful enough to not just predict the road network from some evidence that you're passing, but actually you can learn priors over road networks. So this is a paper from NVIDIA from a couple of years ago called Neural Turtle Graphics. And this actually lets you sample from distributions of map, condition on various things. So you can actually condition on a partial map, and then it will continue expanding, kind of generating from scratch a road network that resembles what you gave it. Or you can even condition it on, let's say, a city name, and it will start generating layouts that look like the city in question. So for example, you can tell it to generate things that look like London, UK, or like New York, or Las Vegas, or whatever. And this can be very useful, for example, for simulation or for stress testing your perception or whatever. Okay, so let's keep going. All right, so these were kind of the high level sort of routing style maps. So now let's look exactly at what we mean by high definition or HD maps. So HD maps, we basically use this term to encompass both the detailed geometry as well as the semantic information of the environment that is encoded within it. And they're used for a very wide range of tasks. So you, of course, can use them to localize within an environment, which is a prerequisite for actually using the information anyway. And they're also useful as prior knowledge for a lot of autonomy tasks, like we saw in the autonomy talks, where a lot of methods can leverage HD map information for things like improving motion forecasting quality, having a good prior on object detection, helping with motion planning, and so on. And of course, for simulation, HD maps can be useful for generating realistic traffic patterns. They can be also useful, for example, for doing sensor simulation, raycasting in them, graphics, and stuff like that. But before we talk about HD maps in more detail, it's important to highlight what the key properties that we want from them are. So when we're building and annotating these kinds of maps, we want them from the get-go to support very large scales, often encompassing very large cities, while also being globally consistent, or as close as possible to globally consistent. And while some applications might require multiple passes in the same area in order for the maps to be complete, so that you kind of cover everything in the environment, even when in one of the passes there are strong occlusions, typically you want to be able to reduce this as much as possible in order to reduce costs. Because if you're relying on passing through a highway 5 times just before you can even start building the map, then that doesn't scale. So there's a lot of methods where you can maybe bootstrap with other modalities like aerial footage, or you can do some sort of in-painting or complement them with some sort of online mapping. And last but not least, You want them to be compact and efficient to deploy, and you want them to only contain the permanent elements in the environment. So you don't want them to be polluted by evidence from foreground objects like pedestrians, cars, and temporary things. So how do we actually build the maps now that we know what we want? So building these kinds of HD maps is a very complex, large-scale process, but you can kind of group some of the tasks into 4 major categories. So in the first step, you need to decide where you actually want to build a map, or what are you actually mapping. So this is called operational domain selection, and it's something that you typically leverage these coarser maps initially in order to select areas of interest for your application. Then once your operational domain is set, then you collect the data in this area. And of course, this can be an ongoing process. It doesn't have to be a pure waterfall. And once you get this data, you process it in some sort of alignment procedure. Maybe you do some offline graph slam or something like this to build like a 3D model of the world that you then can process. And finally, once you have this model, you can then label it with additional semantics that we saw earlier, like the lane information, traffic light information, whatever. And this is done either with the aid of humans or just purely using machine learning models or using hybrid approaches. And depending on the application, you might then just discard the model from step 3, or you might keep it. So if you only need the lane information and stuff, you probably don't need the full model. But if you want to run some fancy sensor simulation algorithm later on, you might need the detailed geometry. So let's talk about these geometric HD maps and what we mean by them. So once we collect this data, there are 3 major steps that go into building these geometric maps. So these are steps 2, 3, and 4 in this illustration. So we begin by splitting the data into some sort of chunks and fitting trajectories to individual chunks. And the benefit of this is that you can do this in parallel, potentially in a distributed manner. So a chunk could be either one driving log, or it can be some sort of submap, or it can be some sort of tile if you're using some sort of GIS subtiling convention. And then you process this data individually, and then you jointly align it into one large reference frame using some sort of trajectory optimization at scale. And then you actually assemble your sensor readings, your observations to build this general representation. So now we need to talk a little bit about what we mean by this simultaneous localization and mapping, or SLAM, from step 3, albeit at a very high level. So SLAM is a very important technology to jointly estimate the trajectory and the 3D map, given this kind of data. And without going into the details, because the details could take up an entire graduate course, let alone a small part of a 30-minute talk, the main benefit of SLAM in this setting is that it can be used to build these large-scale, high-definition maps with little to no prior knowledge on what the world will look like. And you also have the ability to leverage simultaneous localization and mapping to navigate in unknown areas without any maps at all. So we will talk later about online mapping, but in order to make sure that your online mapping is kind of consistently done over time, you need to do some sort of state estimation like this. And of course, there's tons of other SLAM applications that are beyond the scope of this talk, for example, in augmented and virtual reality, headset tracking, and so on. One other aspect that is very important to mention is the ability to handle asynchronous sensors for a reconstruction system. So self-driving vehicles, as one example, are typically equipped with multiple cameras. And this is meant to cover the environment surrounding them with 360 degrees without going to the complexities of very wide angle lenses. And this is pretty common in the industry, but the challenge with this is that the shutters of the cameras might not always be synchronized. So this could be done, this could be just a technical limitations where they're not perfectly synchronized, or it can be by design. So for example, you could synchronize your camera shutters to fire as a spinning LiDAR beam is passing through their field of view. And this is actually a somewhat common setup in common self-driving data sets, because it improves kind of the temporal alignment between the camera data that you get from the cameras and your actual point cloud. And to tackle this problem, there's a range of papers like spline fusion and asynchronous multi-view SLAM that formulate the SLAM trajectory in a way which can incorporate these kinds of observations by basically making it a continuous time representation rather than just a sequence of poses. So there's a lot of benefits to doing this because not only does it allow you to incorporate asynchronous information, But by having this kind of continuous time trajectory for your state estimation, you can also impose additional priors on what your trajectory is expected to be doing. So, it's easier to make it a bit more kinematically feasible, for example. And last but not least, like I mentioned, one final step is that you don't want to keep dynamic objects in this reconstruction, and you want to remove things like moving and parked cars. And these days, this is typically done with semantic segmentation, as we can see in this video for LiDAR, which has matured enough so that it can be used to produce very reliable results at scale without very high computational costs. Okay, so let's talk a little bit about generating the semantic elements of the maps. So on top of geometry, these HD maps contain very rich information, such as location, like the positions of the road boundaries, locations of crosswalks and intersections, and so on. That's kind of encoded ahead of time. And they might also encode more abstract information, like associations between traffic lights and lanes, and how these traffic lights affect specific lanes. However, there are still several challenges that you need to address in order to actually build these kinds of semantic HD map layers at scale. So first of all, the maps change all the time due to things like construction. And in addition, like I mentioned before, it's quite common to require multiple passes through an area in order to build accurate geometric models, even in the presence of occluders. So you want to make sure you control the costs associated with these requirements. And finally, relying on human annotators to hand label the locations and attributes of all the semantic elements in the map is something that is extremely labor intensive and therefore quite expensive. So this motivates the need to build fast, robust, and automated methods for generating semantic maps at scale. And kind of as a bonus, the more progress that is made in this area, the more we can actually transfer this to the online setting. So we can make online mapping more and more robust in order to reduce the reliance on these HD maps. The main idea, though, when you're doing this offline is that in order to overcome the challenges, you need approaches that can leverage both machines as well as humans. And at this stage, humans are still necessary in order to achieve the level of fidelity that you require in safe autonomous driving, which is still beyond the capabilities of pure machine vision alone, especially when it comes to large-scale mapping in potentially very unexpected areas. And generally speaking, scalable self-driving requires approaches where machines and humans can basically collaborate as effectively as possible while minimizing the total cost. And in the next few slides, we will showcase some works where we can actually generate various components of these HD maps using either completely automated methods or methods that can be easily corrected by humans. So let's start with road boundaries. Knowing where the road boundaries are, that is kind of delineating where the drivable surface ends and where the sidewalk begins, is a classic task that is important for safety. And kind of a simple baseline in the industry would be to have human annotators draw these road boundaries from scratch as part of the HD map production. And as I mentioned before, in practice, this is definitely not desirable because if you need to annotate entire cities, this is just not scalable because it's slow. And then in addition to this, you have a quality assurance process afterwards. So if you need humans to click on all these things, and then you need an additional pass just to validate this, then it's just completely unscalable. So the question is, can we actually annotate this process so that human labelers only need to do the quality assurance part, or maybe 1% or at least 5% of the quality assurance part instead of all the labor? And in order to tackle this, we need the models to have outputs that are actually easily editable by humans. So what I'm getting at is we want these models to output formats that are very easily to directly edit by humans in order to allow humans to correct mistakes made by the machine without the need to just highlight gigantic areas and asking other humans to relabel it or relabeling with the model. So one very simple way to do this is to output polylines, because if you have polyline style representations in your maps and your models output this, then your model directly outputs what you have in the map, and humans can just have a UI where they can correct these polylines, they can drag things around, they can delete nodes, they can add nodes, and so on. So in some of the previous sections, we saw methods for computing road networks and their boundaries. And here we will look at a very similar but more fine-grained task, which is estimating the boundaries of all lanes. So the problem can be essentially formulated as discovering and doing inference on a directed acyclic graph, or DAG, as a directed acyclic graphical model, basically. And here your nodes would correspond to geometric and topological attributes. So the idea here is that given some sort of evidence imagery, that could be this projection of your LiDAR, or even similar imagery generated just for cameras, from cameras by mapping from camera planes to the ground plane, we aim to find the best DAG that can describe the road. And the space of all possible graphs is gigantic. So the idea here is to bypass some of these complexities by using greedy approaches, where we essentially construct a graph incrementally by using neural networks to always predict the next vertex. So in a method like this, the inference process can be highlighted, can be described using the example on the right, where on top you start with the half-done DAG, and then you have the direction of the next vertex that gives you an ROI. And then by taking that ROI that's highlighted in the box and feeding it to a model, the model will then predict the exact coordinates of the next node, as well as the attributes of that node. And then in this case, you compute the location of the node that's highlighted there with the big blob, and then the network classifies that as a fork. So what the fork means is that essentially the lane conceptually splits over there. So then you'll continue iteratively drawing the current one, but you make a note to return to that fork once you're done with the current line and draw the next one. So this is kind of similar to how a human would annotate this. So here's a video that showcases some of the benefits of, or some of the capabilities of a model like this, which can work on, multi-lane roads. It can do it can do forks, it can do merges on highways, and it can also operate quite well in city environments and in intersections and so on. And in a slightly similar but still a bit different direction, instead of thinking about things in terms of lane boundaries, you can also parameterize things in terms of lane segment center lines. So methods like centerline that basically create global maps of center lines by first predicting lane center line segmentation masks, and then using some sort of transformer or any other kind of inference to then iteratively predict the actual vertices. So in a way, this is a neural network that encompasses the techniques we saw for the topological map creation in the beginning, except now this is all inside a neural network, where you start with the segmentation and then the neural network itself figures out the polyline representation of this. And of course, the models that I showcased here are just very, very few examples, because this is a very rapidly moving field. So there's tons of other approaches in which you can map various attributes separately or jointly. So there's a lot of papers coming out pretty much every day on this topic. So with that being said, let's now switch gears away from building maps offline and focus more on online mapping. And we have a question on Zoom that is basically just that, which is, would it be feasible to build an autonomous car that doesn't rely on maps, except for street information for navigation, of course. And online mapping will be definitely the way to go in that direction in the future. So online mapping is a must for safety, because maps are not always up to date, and localization itself can fail. We might not have a map in an area, and so on. So we kind of talked a bit about these topics both in the perception sections as well as in motion planning. If you remember the motivation for papers like the mapless occupancy field driving and so on, where it's important to account for the fact that the vehicle still needs to reason about the structure of the environment without knowing exactly what the map looks like ahead of time, except for, again, high-level routing. So examples of challenges, of course, are construction. That everyone can relate to, where you can have a lot of different effects from construction. So you can have roads that get only partly closed. Maybe a road gets completely closed. Maybe a bike lane gets closed, so your route doesn't get affected, but then there's a higher probability that bikes will get in your way, and so on. So online mapping is definitely really important for safe, scalable autonomous driving, but of course, it also comes with its own set of challenges. So as mentioned previously, occlusions are a big factor because mapping elements can now be occluded by objects in the scene, such as vehicles and pedestrians, and we don't really have a way of seeing past these occlusions directly. And compared to offline mapping, online mapping also can only really detect things that are within the range of the onboard sensor. So you cannot just, do a drive in the entire operational domain, build a nice point cloud and process it. You have to do it online and live within the limitations of your sensors. And as we saw, construction elements like cones, construction vehicles, and so on can alter how the map is perceived by the self-driving car. So detecting them is crucial, but it's also important to understand their meaning. So how do these cones actually affect my driving path, not just which points are cone versus non-cone. And for autonomous driving, the software stack itself must also run very efficiently. So online mapping must run in real time onboard the vehicle alongside everything else. So you have a bit more of a strict computational budget in this sense. And finally, it's very important to create consistent maps over time, which is challenging when you only get your observations incrementally. So you need to make sure you're kind of fusing this information over time in a consistent manner to avoid conflicts, to avoid flickering and so on in your internal online representation. So to do online mapping, there are many papers which, for example, tackle this within the camera space. So maybe they use camera imagery and they tackle the task from the 2D camera space. And for example, do some sort of segmentation with deep learning. You get, for example, lane boundary pixels, and then you might want to do something like clustering the pixels and then fitting some sort of geometry to each pixel cluster. So this is a classic example, for example, for lane detection, where you fit some lines or some splines to these points. But it is important to highlight the fact that doing some perception task accurately in 2D doesn't necessarily mean that it is easy to extend this information into 3D, which is really the space you care about, because that's the actual space that the vehicle is moving in and planning in and so on. So this is a simple example that's meant to highlight this issue. It also applies to other kinds of things you might want to map. So the idea is you have the input camera image on the left, and you then, in the second image, we show the lane boundary probabilities in the camera image. And while they look good in the camera image, because of how perspective projections work, once you plot these probability maps into 3D, you see that the lane boundaries basically become very fuzzy, farther away from the vehicle, which might cause difficulties with motion planning. So detecting things in 2D can result in issues and inaccuracies in 3D, which kind of motivates the need to not have the 3D part of things as an afterthought, but to always, even when you're just using a single camera as input, to really try your best to do all of your reasoning in 3D. Because this is where the autonomous vehicle is operating fundamentally. And perhaps more at an engineering level, in my experience, it's also very, if you're prototyping something, it's also often tempting to reason about things in 2D initially and think about, I'll make it 3D later. But it actually is very, very beneficial, even if you think it might be a bit of a hassle, to start thinking about 3D from day one, because they will avoid a lot of headache later down the road. There's going to be a lot of geometric code, a lot of processing code that you need to make sure works correctly if you decide to port later on to 3D. So there's a lot of papers that do this kind of perception in 3D. I'm going to kind of skim over some of them because the specifics are not very important and they're changing all the time. One interesting family of work is something that has been also covered in a couple of previous talks, which is papers like Lift, Splat, Shoot that actually use multiple cameras or multiple of these sensors to reason about kind of online mapping plus semantics, or mapping plus perception in a non-parametric way. And this paper, Lift, Splat, Shoot, what this does cool is that it has this architecture that allows features from 2D image feature maps to be fused in a bird's eye view top-down representation that is beneficial for tasks like planning. But the method can do this fusion without necessarily reasoning explicitly about the depth of every pixel. And instead, it can take depth uncertainty into consideration when fusing this information. So this allows for the results to be very robust, and the method can actually be used for the task of planning as well. So here's an example of the results. The method uses 6 cameras on the left, and you can see the bird's eye view online maps on the right, where it can segment things like the roads. It can segment out areas that contain cars and pedestrians and so on. Other methods are things like HDMapNet. It's a similar method, but instead of using these ray casts, you instead use purely learned projections to take camera features into this top-down bird's eye view. And then again, you fuse this feature with deep LiDAR in the case of this paper, although that's generally optional. And you output your semantic segmentation map, you output instance embeddings, direction maps, and so on, and then fuse this information into something that you want to use downstream. And as shown in this video, the results are very crisp, and there's very little flickering going on. So it's a nice output space to use. And another bonus of this is that you can then take single frame predictions. And if your state estimation is smooth and consistent enough over time, you can actually fuse them temporally in order to build large scale maps. And as we saw in a couple of the earlier talks, mapping itself is just a means to an end. So there are papers that actually learn representations that are optimal. They learn map representations that are optimal for the task of driving itself. And one of these papers is the recent MP3, which is an end-to-end networks that tackles this task of online mapping and learning kind of perception and driving. And its name stands for Mapping, Perceiving, Predicting, and Planning. And it's able to leverage online mapping, object detection, future forecasting together in order to drive in novel, completely unmapped, unseen scenes. So to wrap things up, we discussed the two types of maps that are typically employed in self-driving, which are topological maps and HD maps. I then showcased a little bit how to develop algorithms where humans and machines can work together in order to build these HD maps. And we looked at a few approaches then for online mapping and how they can be used to reduce reliance on these prior maps and improve the scalability of autonomous driving. Thank you very much for your attention. I've skipped over a lot of stuff. A lot of you are probably shaking your heads because, for example, I was mentioning human robot sort of collaboration, but we didn't even have time to talk about active learning or reinforcement learning. So those are also areas where you can actually enhance joint sort of hybrid methods where models and humans can actually make the most benefit from each other. So there's a lot of stuff that didn't fit into this talk, but we will continue with localization because you need to do localization in order to actually leverage prior map information. So that's going to be the next session. That's going to start in like 1 minute. But for the time being, thank you very much for your attention. I think we have time for one question. If there's a slight bit of time, and then I'll, if anyone has a question, go for it. Yes.
Hello, thank you for your presentation.
I think so. I can hear you loud.
So apparently we were moving from the past years from individual tasks such as detecting the lane, detecting pedestrians, detecting online mapping. What are your thoughts? What's your opinion about? Apparently, we're moving forward to reduce a lot of computation and put all of these tasks into a single big model, and maybe append in that model little heads with the particular task. Is that the way you're seeing of the future autonomous driving setup?
Yeah, sure. So the question was basically about kind of unified architectures and this trend of going towards kind of a shared representation that is then used to decode the map information as well as the perception and driving and so on, right? And whether I think that's kind of the overall trend. And that's a very good question. I think it's still a little early to say what the long term will look like. I do believe that multi-sensor fusion backbones can be very important because they can save a lot of computation. I've also seen papers which they completely learn the sensor fusion. So for example, you don't even need to do geometry for the cameras in order to fuse them with LiDAR. So there's papers that do like transformers that just learn from nothing how to like fuse information from between LiDARs and cameras and end up working surprisingly well. So I think there's a lot of benefit there to fusing this. And then in terms of the outputs, I think it's still a little bit early to tell, like I said, but there's definitely a lot of benefits in non-parametric outputs, just because even though they're less compact, they let you reason about very uncertain things without kind of thresholding them out like you would if you have a box output. So I think there's definitely a lot of potential in that area for these unified methods. Yeah.
Thank you.
Yeah, you're welcome. So yeah, and then to talk a little bit more about maps, I definitely think it's possible to have both. So you have some sort of HD map and perceive the map online. And then you can fuse this information, and then you can have models that basically learn how to do conflict resolution, just like a human would, basically, where you figure out what information is more reliable and then you use that.